So it's my pleasure to introduce Louis Kauffman, who's going to be talking about reconnection numbers of non-related sets. So thank you very much.
Okay, should I start?
Yes, absolutely.
Okay, here, I'll share a screen. And there's the screen, and let's see if we can get the view there. Okay, we can begin. Just occurred to me that the design that I used on this first slide is similar to the CMAT logo, except that in the CMAT logo, you have a Mobius strip. No, you don't have a Mobius strip. You have two half twists, and you have it folded over in such a way that we see both sides. But this knot is a Mobius trefoil knot, produced by Escher with three half twists, one here, one there, and cut down the middle so that you see the knot. So maybe that gives you something to think about while we talk about other things. So a little reminder about things in knot theory. We're concerned with whether things are knotted, of course, and when you have something a bit complicated like this, it isn't immediately obvious whether or not it's knotted. As a matter of fact, this one isn't knotted. It can be smoothly isotoped until it's just a circle, but you might find that a little difficult. I won't have time in the talk to do it for you, but if you're interested, we can look at it later. And of course, there's linking. And there's subtle linking, like in the Borromean rings, where the three are linked, but any two of them are unlinked. And there's the trefoil knot, and illustrated here, just for the sake of some background, is one of the simplest proofs that the trefoil knot is knotted by coloring its arcs with three colors and then seeing that an appropriate set of rules for continuing to color other versions of it will retain the three colors. The extra rules are, what you see is that three colors should appear at a crossing, and the other rule is that it's possible and allowed that one color could appear at a crossing, but not two. And then you can, excuse me, then you can verify that every trefoil knot that it inherits from this one by an isotopy will still be three colored. Now here's a bit of history. There's lots of history to knotting, of course. This history I chose with some malice aforethought because it's interesting to see that Mr. Romilly Allen, back around 1900, in writing a book on Celtic art, came upon one of the same kinds of decompositions at a crossing that we find useful, and that is part of the theme of this talk. So Romilly Allen pointed out that you could start with a regular lattice weave like the one on the right, and then you could remove some of the crossings by connecting them up either horizontally or vertically, as illustrated here in his slide. You can attach A to D and C to B, or you could attach A to C and B to D, and then you will see that you get some interesting knotting patterns. And and by choosing the ways to eliminate the crossings, you get all sorts of knots, and those are one of the ways in which people created the Celtic knot patterns. But this decomposition of a crossing into two ways of smoothing it, or two ways of reconnecting it, like this, turns out to be a good idea for getting knot invariance, where the idea for getting knot invariance is more mathematical. You say, I have a knot diagram, and I'm going to reconnect it one way, and I'm also going to reconnect it the other way, and I will add up over all the possibilities. And with appropriate coefficients, that turns out to be an invariant of the knot. Appropriate coefficients and normalizations. And this sum over states is the machinery behind which some of the things I'm going to talk about are based here. Now, indeed, we also are going to be talking about physical reconnection. And vortices can reconnect. That is, it's possible for vortex lines to come near one another, undergo some chaotic interaction. That is to say, undergo some interaction that we don't fully know how to model, and end up like this. That's very interesting. In order to do so, you have to put some orientations on the thing because the vortices are going around in a certain direction. And so it isn't true that any two vortex lines might do that, but two vortex lines that are appropriately oriented can do that. Here's an example of calculating with this kind of an invariant. You start with the knot, you smooth crossings and add them up, but you're not done because you have to do it some more. And you smooth the crossing here. And then these three end states are good enough because we already know what happens with a twist. It multiplies by something. And then we can add it up and get a polynomial. And the polynomial, once it's normalized, has the property that if the mirror image of the knot is calculated, it will be the result of putting A for A inverse in the polynomial. So if the polynomial is not symmetrical under the AA inverse interchange, then the knot is not equivalent to its mirror image. And so we get a simple proof that the truffle and its mirror image are distinct from one another in this way. All of the calculations that come out of doing these reconnections lead to 2 to the n possible configurations from the given knot because you get to choose 2 for each one of the crossings. So there are 2 to the n of them like this. And the polynomial is actually calculated by taking the products of the choices that are either A's or B's and the number of loops in each one of these states. So the states actually determine the polynomial. And there's another invariant. I'm just giving you a survey of machinery before we start to talk about things a little more physical. There's another invariant discovered by Kovanov where he said intelligently, you could put an ordering on these states, starting with all A's and ending with all B's, where an arrow means a change from an A type to a B type. So each of these is a reconnection, sequences of reconnections like that. And then he said, but it's a category, and categories have homology, and plugs into certain kinds of machinery about homology of categories and produces an invariant that is a homology group associated with the knot, which can be specialized to produce the original knot polynomial, the Jones polynomial or the bracket model. And this turns out to be a very good technique for thinking about some of the kinds of problems that we're going to think about. We're going to be thinking about the kind of problem that says, well, how many reconnections would you need in order to unknot a knot? And you can see that since this contains all possible reconnections, including the ones that are not allowed in our physical situation, it might contain some information for us. It does. But I don't want to go into further details about that homology theory. That would be another talk. We'll skip that for sure. I wouldn't have used it if I hadn't been out of my slideshow. There we go. Let's get out of the slide and get back into the slideshow. So what I'm going to talk about is knotted vortices and reconnection in vortices. Now, it's an old story going all the way back to Lord Kelvin that Kelvin had a theory that knotted vortices in the luminiferous ether were atoms. But the luminiferous ether suffered a decline after special relativity, particularly. And, and so, as a physical theory, as a kind of early string theory, this didn't work out. But people continued to study the possibility of knotted vortices in fluids, but it wasn't until 2012 when Irvine and Kleckner actually produced knotted vortices in water by an experiment. And this is a photograph of one of their knotted vortices. So I wanted to tell you or remind you how they did that. We don't have to use the slide about Kelvin. I just told you about him. But this is some of the drawings that Kelvin had for atoms way back then. And other people at that time were fascinated by the theoretical idea of material world coming from a patterned world by means of things like knots, and thought it was a spiritual matter and drew their own knots. And later on, for example, in the 70s, Herbert Yale had a theory that um, knotted quantized flux would be elementary particles. It was a qualitative theory, but a precursor in a way to string theory. And now we get to Kleckner and Irvine. And what did they do? Well, they make vortices in water by using these foils. The cross section of this circular foil is a little teardrop so that vortexing can happen at the upper sharp point of the teardrop, which is an upper circle, thin circle. The thing goes down through the water flows up over the entity and vortexes as it gets pulled off from the top. You pull that object down through the water and it will produce a vortex. Well, if you can produce a vortex that way, why not produce a knotted vortex by knotting the template? And that is what they did. They used knotted templates of the same kind and pulled them down through water, used good technique of high speed photography, and could see the vortices. So here's their film of an unknotted vortex happening. And here's their film of a knotted vortex happening. You can see the truffle knot quite clearly there. Now, these guys are very unstable, and in fact, they tend to decompose exactly by reconnection. Here's a picture of some of that kind of vortex undergoing reconnection. It starts out over here parallel to itself, undergoes some complex interaction, and ends up reconnected the other way. So we want to make a model of reconnection and then ask what's the least number of reconnection events that would be needed to undo a knot. Now, it's also the case that you can do experiments in the computer with these by using physical fields in the computer. This is an example of the kind of work that they do and that I happen to be on one of their papers, where they use a nonlinear Schrodinger equation, the Gross-Piatowski equation, and they let the vortices are singularities in the phase of the wave function of this non-singular wave function of this non-linear Schrodinger equation. So it looks like this. The phases are changing around the vortex. And you can use a computer to watch the vortices and watch them undergo reconnections. So you can do experiments like that as well. And you will see sequences of events like that. So now let's go back to how would we model this in as simple a way as we can so we can think of it in terms of combinatorial topology. Well, the vortex is going around the vortex line, like these little circles are going around my vortex lines here, going around like that. And if the vortices are arranged in such a way that the vortex directions in between the vortex lines are the same, then the fluid is flowing between the two vortices and the vortices can pull together and then they can undergo reconnection. Those are the conditions under which it can happen. And so if we decide to orient our topology lines by the right-hand rule, then we see that the correct condition for having a reconnection is oppositely oriented vortex lines going up, going down. And then it's convenient to see that when you cut and rejoin, there's still oppositely oriented lines. So that's the rule that we're going to follow. And now we're asking, given a knot or a link, what's the least number of such reconnections that are needed to turn it into an unknot? Now, one thing you can do if you have a diagram is you can go near a crossing. And near the crossing, you see that there's an arrow going in and an arrow going out. So you could do a saddle, you could do a reconnection right there and go here. That's one. And then you see that you have a link. So you have to do at least one more in order to get down to an unlinked thing or an unknotted thing. And one more is sufficient. So you can do it in two, but that doesn't prove that two is least. In order to prove that two is least, you have to somehow confront the infinity of configurations that that knot can represent and understand that it's not possible in any one of those configurations for two lines to come near one another and undo the knot in one reconnection. So you need topological invariant things to calculate in order to do that. But nevertheless, in terms of making examples, the idea that at a crossing we can do a reconnection just like that is very important. So that's our model, local surgery to make the reconnection. And here's another experiment from that paper. I thought we had a movie there. Well, didn't want to run, but doesn't matter. The movie shows you starting with 6-2 here, and then undergoing a reconnection at a crossing, and it becomes a link, and then it undergoes another reconnection and becomes a trefoil knot, and then two more undo the trefoil knot, so that you end up with 4 reconnections to undo that fellow. Oh, I see. I forgot that I wasn't in my slideshow. You might as well watch it. Okay, so that's 6-2. Now I want to tell you a little more topology about how I'm going to think about this. I want to think about a reconnection as an event in space-time, idealized for the sake of topology, where the two vortex lines come together, go through a saddle point and pull back apart, so that what's traced in 4 space is a little saddle surface, as you see in the upper part of this diagram. And it could go up or it could go down, as you see. And then we call that an elementary cobordism of knots. And other cobordisms that we like to consider are births and deaths, where a circle is given rise to out of nothing, or a circle dies and becomes nothing. And when you go through a series of these, you trace out a surface. And the surface can be thought of as in 4 space, or you can just look at the genus of the surface that you get as a result. But then you can see that the genus of the surface is closely related to the matter of reconnection, because every time you go through a saddle point, every time you go through one of my saddles, you do a reconnection. And so every hole in the surface needs at least 2 reconnections. So you can count two reconnections for every genus that the surface acquires. And then you can watch these surfaces to see how they behave. So for example, in the case of the trefoil, we went through one saddle point and ended up with a link of 2 components. And then we rejoined them with another saddle point and ended up back at a single curve, which was unknotted. And the surface that was traced in 4 space, if you like, it was a genus 1 surface. It's a torus. So the question that knot theorists know a little about is some bounds on the least genus surfaces that cobordisms could have. And the genus can be thought of as telling you about twice the reconnection number. So if you divide the genus by 2, you have an estimate on the reconnection number. Now, getting back to 6.2, our example, this is how it ended up with 4. It went through a saddle here, then it went through a saddle up there, I went through a reconnection there. We ended up with a trefoil, and then 2 more from the trefoil got it down. It seemed to need 4. Curiously enough, it doesn't really need 4 from the topologist's point of view. It might need 4 in that physical system. We don't know. More experiment would be needed. But here's the thing. Here's a nice lemma for the mathematics. If you want to switch a crossing in a diagram, you can do it by 2 reconnections. And here's the story. You start with the left-hand crossing. You start with the right-hand crossing, in this case. Start with that one. You put a little twist in it, so you have an arrow going down this way. Now these 2 can reconnect. They do reconnect. Now you pull it out, you push it back over, you undergo another reconnection, and you get rid of that twist, and you're over here. So you see, I managed to produce 2, by 2 reconnections, I switched to crossing. So that's a good thing to know, because if we were to take 6.2 here and look at it carefully, we would realize that 6.2 can be undone, made unknotted by 1 crossing switch right there. Switch that crossing, and now look at that. You see this pulls out over, and that comes under, and the whole thing is unknotted. So 6.2 only took 2 reconnections. It didn't require 4. And that leaves us with the question, what about that physical system from the nonlinear Schrodinger equation? Maybe it really needs 4 to underdo 6.2. Not going to do it so efficiently as the topology did. We don't know. It would require some more experiments. Here's what it would look like if you had 6.2 doing that in context. Here's the 6.2, and I'll get my pointer again. Here's the 6.2, and right here we went through a reconnection. Then this pulled back and went back over and reconnected, and this is now unknotted. That's how it would look if it happened. So we've seen that a physical sequence of reconnections takes 6.2 to the unknot in 4 steps, but in principle, it can be done in 2 steps, and this requires more investigation. Now, what about lower bounds? Well, topology can give you some lower bounds, and some more elementary topology than the Kauffman homology that I mentioned at the beginning will give you some lower bounds. They aren't the best lower bounds, however. They are good lower bounds for the trefoil and the 6.2. It comes from the signature of the knot. There is an invariant called signature of the knot, and it satisfies the following theorem, that the absolute value of the signature is a lower bound on the reconnection number. So when I calculate that the signature of the trefoil is 2 in absolute value, then that proves that the trefoil needs 2. And this is done by a theorem of Murasugi, who showed that the signature is a lower bound on the twice the 4-ball genus. And as we said, genus and reconnection number are related. So you might be interested to see how signature gets calculated. I just say it briefly. You take a surface whose boundary is the knot, and you look at a basis of curves on that surface. And those curves can intersect one another, but we can measure the way they link one another in 3 space by using the positive normal to the surface and pushing one curve upward a little bit and looking at its linking number with the other curve. So if I push B upward and look at its linking number with A, there's no linking number. But if I push A upward, then I get a linking number between A and B. That corresponds to the off-diagonal entries here of 0 and 1 in this matrix. And then there are self-linking numbers obtained in the same way. And these linking numbers up to an appropriate, this matrix of linking numbers up to certain equivalences given variance of the knot. You can calculate the Alexander polynomial, and you can calculate the signature. You calculate the signature by symmetrizing this non-symmetric matrix, taking theta plus theta transpose, and taking its algebraic signature, which is essentially equal to the number of positive minus the number of negative eigenvalues. So this is a direct way that you can get some estimates on the reconnection number. But as I said, you should be warned that these are not necessarily the best. However, the surfaces that span the knot are important in other ways, and here's one way in which they're important for us. Here's a trefoil knot. Smooth all the crossings by connecting them in such a way that they are orientedly connected. Now you see oriented in the same direction at every crossing. You get a collection of circles in the plane, and Seifert intelligently pointed out that if you span each one of these with a disk and put in little twisted bands where the crossings were, you get an orientable surface whose boundary is the knot. So the genus of that is an estimate on can be twice the genus of that as an estimate on the reconnection number, but it won't necessarily be very good. The reconnection number could be considerably less than that. However, you can think of this in terms of cobordism, and that's important. So yeah, I can get to the same Seifert surface by cobordism. I have the ingoing arc and the outgoing arc, and I do a reconnection right there. And I do that at every crossing. Then I get the Seifert circles all over again with little twists in them. You see? So if I then bound them with disks off into the 4 space, I get the Seifert surface now pushed off into 4 space. That's an example of a surface in 4 space that's obtained from the knot diagram that is the Seifert surface, actually. So the Seifert surface appears in our cobordism thoughts. And you might wonder, well, what is the genus of this surface? And I just tell you the answer. The genus of that Seifert surface turns out to be equal to 1/2 of the number of crossings minus the number of Seifert circuits plus 1. We're going to see that number again in a moment. But in this case, the number of crossings is 3. The number of Seifert circuits was 2, so we're subtracting only 1 from 3, making 2, and dividing by 2, we get 1. It's a torus surface. And that's telling us that the reconnection number should be related to 2. That's our estimate, as we knew from before. But now we have the following result. Let me go back to my slideshow. Oh, we don't want to go back to it there, do we? Sorry. It's good to point. But that's the theorem I want, and I didn't want to bother you with another theorem. So here's the theorem. You have a positive link. That means that all the crossings are positive, which means that the crossings all obey the right-hand rule. Maybe we have an example of a crossing. Here, all the crossings in the trefoil knot are positive. If you put your fingers in the direction of the overcrossing line, your thumb goes in the direction of the undercrossing line. That's a positive crossing. So if you have a knot diagram with all positive crossings, sorry. My slideshow jumps around a little bit when I go back and forth, so maybe I shouldn't. Oh, I'm sorry. Pardon me. I'll just go this way and stop jumping back and forth. There we go. All right. So if you have a positive link, then the 4-ball genus of the link is equal to the Seifert genus for any positive diagram of K. So the Seifert genus actually is equal to the genus under certain special conditions, positive link. But these include a lot of knots that we might be interested in for physical reasons, like torus knots. If you take the right mirror image of a torus knot, it'll be a positive knot. And you can draw lots of positive knots, infinitely many of them. And that means that the reconnection number must be greater than or equal to twice the four-ball genus, which is the number of crossings minus the number of Seifert circles plus 1. This comes by using covariant homology and what's called Rasmussen's invariant. So there's some nice combinatorial topology that gets you this, which we don't have time to do in this talk, but we can go further and say that it actually is equal to that. And this we can show you because what do we have to do? We can rest on the theorem that we had on the previous slide, which says that it's greater than or equal to it, and just produce an example where it happens in exactly that many events. And then we're done, right? Then it must be equal to it. So that's what I'm going to do. I'm going to actually produce a sequence of events that unknots the knot, the positive knot, in that many moves. Actually, I can unknot any knot in that many moves, but that isn't necessarily the reconnection number. It's that it's lower bounded by that gets it. So here's our positive knot for purposes of illustration. And here's this, I will go back to pointing. Here's the Seifert circles. All the way to the Seifert circles, of course, I'm unlinked, but this is very inefficient if I went all the way to the Seifert circles, because I could have connected these up. If I connected this up and didn't do anything to that crossing, then there would be just a little twist there. And then there would be another little twist there. And then I hang it on this one and another little twist. And I make sure that I do this forming a tree structure. And I end up hanging all the Seifert circles out in the form of a tree, in this case, a linear tree. And there we are. There's my tree. And here are the reconnections that I did, but I didn't do all the reconnections. The knot has 10 crossings, but I only did 6 reconnections because 1, 2, 3, 4 of these were not used. And so 10 minus 4 is 6. And why 4? That's 1 less than the number of Seifert circles, because I can connect the Seifert circles together with 1 less than their total, right? First to second, second to third, third to fourth, fourth to fifth. 4 connections. 4 connections by ordinary crossings. So you see that it is tautological that I can do C of k minus S of k plus 1 reconnections to turn the knot into an unknot. And actually, this is true in general, but in the case of positive knots, that comes right up against the lower bound, and we therefore know the reconnections numbers for any positive knots. And this means that we're in a position to do some more experiments if we would organize ourselves to do so and see what the physical situations would look like in relation to the known reconnection numbers. So that's the story. And I see that we still have a little time. So you might have a question at this point. Let me open the floor for questions. Okay, let's continue with another couple of examples. Here's a link.
Sorry,
Yeah.
we
Yeah.
have muted here, so there is a question here.
Hi, I was wondering if you had a lot of non-essential crossings, is there some upper limit on how complex it could become through reconnection?
Let's see. Let me stop sharing for a moment. Now, what was that question again?
If you have a vortex with a lot of non-essential crossings, is there some kind of upper
A
bound?
non-simple crossing?
Non-essential, nugatory?
What I'm not sure what you might mean by a non-simple crossing. You might mean, let me get a piece of rope
I
here.
don't think he said non-simple, he said something different. What was it that you said?
Non-essential.
When you say when most of our crossings look like this, right? They just one bit of rope going over another bit of rope like that, right? But sometimes people are thinking about multiple crossings like that, where you have many crossings happening at once. Is that what you mean by non-simple crossing?
He didn't say non-simple, he said non-essential.
Non
Non-essential.
non-essential.
Don't worry about
What does non-essential mean?
it.
A
Nugatory,
non-essential might mean that you can see immediately that it can be undone like that. But that's all right. We consider all diagrams when we do invariance. Some of the crossings are non-essential in that sense. You may have a different physical idea there than the one I'm suggesting.
I think there's a problem with, maybe we should ask the people who are asking questions to come down here physically to the laptop so that he can hear correctly. I don't think he was able to hear the question very well with the microphone. Yes, but he was not, pero no estaba entendiendo las palabras bien de. Okay, it's okay. We can. Oh, we can continue with the talk if you like.
Okay, we'll continue. So here, there. So here's another example. It's interesting to just look. Here's a link, and the number of crossings is 4. The ciphered circles, I've made them. There are 3 of them. So C minus S plus 1 is 2. So this says that I can do it in 2. And then I might look at it and think, I think I'll do a reconnection right there. That's natural. But now I'm going to need, two more reconnections to get those links to become undone. Each one requires 1. So it'd be up to 3. So this can't be the most efficient way to do it. Our method shows you a way to do it, because we would do a reconnection here and another reconnection there. And then we have an unknot. And that was the one that used 2. But we didn't break it apart. So it's interesting to see how, the topological solution might not be the one that you would think of, or the one that the physical system would think of. Quite possibly not. Let's make a few more remarks here. Here's a torus knot. Now, in the case of the torus knot, here are the ciphered circles, all parallel to one another, and there are 3 of them in the case of a 3-4 torus knot. And you can check in general for a PQ torus knot, P times around one way and Q times around the other way, that the C of K minus S of K plus 1 is equal to P minus 1 times Q minus 1. So we get that the reconnection number is the product of P and Q divided by 2, which in this case is 6. So this has reconnection number 6. And we know the reconnection number in general for torus knots. I won't bother you with this slide, or this one, but people have studied cascades of reconnections, and you can take these cascades that have been studied, if they started with positive knots like a torus knot, and compare how things worked in terms of least numbers. So time will tell what happens to these results, but they're clearly useful results. Let me tell you a little bit about Kauffman homology, just so you get an idea about it. As I said, he has the idea of a category here, and he's going to up-level everything to study this category, this arrow pattern associated with the knot diagram of all oriented and unoriented reconnections. And then, in order to think about the topology of it, I wanted to tell you another idea. The other idea has to do with what I call virtual knot theory. And in virtual knot theory, I restrict my knots to winding on a surface, like your clothes is woven on your body. And you could think of a virtual vortex, but I don't have a physical example. If you had a virtual vortex, then there would be places in the vortex where it wouldn't be available to do a reconnection because the points were far away from one another. You see, when I make a sketch drawing of a virtual knot like this, these points are likely to be way across a surface from one another. So they're not available for reconnection. Other places are available for reconnection. We can do the same kind of work that I did before, and we can find out bounds on reconnection for virtual vortices. But the question is whether some modification of this abstract idea of a virtual vortex might be of use. So that's a question I'm raising. Now let's go to the covariant homology. The covariant homology is a very patterned thing and asks you to go back to thinking about things in a way that you haven't thought about since the 1500s. For example, you think of a plus b cubed and you're well trained in algebra, so you know it's a cubed plus 3a squared b plus 3ab squared plus b cubed. But when we did the smoothings to get the states of the trefoil, we had 3a's, we had 3b's, and all the intermediate states, and we're looking at a arrow b cubed. Every one of these arrows has an a going to a b. We're looking at a category associated with a and b cubed, and we're looking at the structure of the cube as it's decomposed. So these arrows actually correspond to where the blocks in that cube meet each other. So, and this goes up into higher dimensions. And we're using this kind of structure to get at the knot theory. And in order to do so, I skip some things. In order to do so, we do think of the arrows in the category as being cobordisms. We think of going from an A to a B, or which I call the inverse here, as being a saddle, going through a saddle. We think of it that way. And then we have to look at how one category looks in relation to the other category when you have a move that you made. And so then you start thinking about things like this. Here's one category which is very simple locally, and here's the other category that corresponds to this Reitermeister move, where you had A's and B's and so on, more complicated. And how do you compare them? You can compare these parallel lines with these. You can actually compare this one to this one if you use a cobordism idea and allow yourself to give birth to a circle. You can go from here to here by giving birth to a circle. You can go from here by letting a circle die. You can go from here to here by doing a reconnection. So a combination of reconnections and births and deaths and thinking in terms of cobordisms gives rise to ways to compare these categories, and that ends up giving rise to algebra that allows one to do the homology theory. So I just wanted to say that much to you so that you get a little bit of a feeling for what this kind of a theory looks like. And then I want to go off in my slideshow to something else, which I think is really amusing. And that is an experiment by Alexienko in 2016 in Novosibirsk. And he showed that it may be quite possible to switch a crossing and make the topology more complicated in a real physical situation. In fact, he shows it happening for a vortex in a turbine. It's a turbine vortex. There's a turbine up at the top of a long tube, which gets wider as it goes down to the bottom. And you're going to see the vortex moving upward a little bit and then undergoing recombination right along there and ending up with a link. So you go from simpler topology to more complex topology. And if my system doesn't jump, it didn't jump. Here's the movie, which goes too fast. But maybe you saw it. Anyway, I have the frames. Here we are. The vortex moved upward a little bit and underneath. Then it moved upward a little farther, comes nearby itself, and you'll notice that if we oriented this downward, then we go all the way around, that's oriented upward. So these can undergo reconnection, and they do. That's the best detail I have for the reconnection. The next shot is reconnected. And there you have a link. So this is showing that it certainly is possible in some physical systems for the topology to become more complicated. And so you could wonder about producing all kinds of weaving through reconnection if you wanted to think about that. And I'll stop there.
Thank you very much. Are there any questions for our speaker? Yes, we do have a question.
Have you related the reconnection number to any other non?
Could you repeat that, please?
Sure.
He wanted to know how can you relate the reconnection number to other non-invariants?
Well, as you see, in this case, I'm relating the reconnection number to the least genus surface that it bounds in force space, and that's related to signature and it's related to Rasmussen invariant. So those stories can be looked at more carefully, of course. I just was going over the surface of that.
And I maybe have a quick question also. What is the physical motivation of the nonlinear Schrodinger equation that you mentioned?
Well, I don't have the complete story on that, but people have used that nonlinear Schrodinger equation for a lot of vortex modeling over the last 20 years. It's a standard thing. It's the nonlinearity that allows the evolutions of the vortices to happen, and it's related to superconducting.
Any other questions for our speaker? Well, if not, then let's thank our speaker again.
Okay,
Thank you very much, and sorry for the technical difficulties there.
no problem. Thank you very much. I'm happy to have been able to talk to you.
Yes, thank you for speaking.